Hi, welcome back to my channel. The ongoing energy deregulation has created various job opportunities in the energy sector, including positions like energy trading, energy market design, and energy market optimizations. In this video, I'll discuss 10 questions that you will likely see in an energy market job interview. Knowing how to answer these questions will show your understandings of the important energy market concepts and may increase your chance of being hired. However, please remember that you should never remember the sample answers mechanically because they're not meant to be standard and exhaustive. You should always understand the concept being asked and be able to describe them in your own words during an interview. Keep your answers relevant and concise. After answering each question, you may ask the interviewer if your answer fully addressed their questions. Be ready to defend your answer and elaborate if needed. Now let's get started. Question number 1. Describe your understanding of the optimization in the energy market. It is not very practical to expect you to know every technical details about the energy market optimization. However, you should, at a minimum, understand what the optimization does and the key inputs and outputs. Simple answer. The energy market optimization refers to the process of committing and dispatching the most economical generation to serve the forecasted load while honoring various grid constraints. They include resource constraint, transmission constraint, ancillary service, as well as regulatory constraints in the market. The optimization itself uses the load forecast, generator schedules, bids, transmission topologies, etc., to calculate the optimal generation outputs, energy interchanges, and locational marginal price in the grid. Mathematically, the optimization is a large-scale mixed integer problem solved continuously by the market operator. In the United States example, it's the system operator, or ISO. Question number 2. Explain the concept of locational marginal price, or LMP, and its components. LMP is one of the most important concepts in the energy market. You should know what LMP is. For example, it's a shadow price, not a total cost. Also, explaining each LMP component accurately will further show your knowledge of the concept and suggest your ability to analyze LMP to reach meaningful conclusions. Now let's look at the sample answer. Locational marginal price, or LMP, is a pricing mechanism widely used in deregulated wholesale electricity markets to settle energy purchase and sales. LMP represents the incremental cost to serve the next megawatt of load at a specific location, considering factors such as transmission limits, generation capacities, and losses. The most common components of LMP include the energy component. This is the marginal cost of producing one additional unit of electricity to serve the system load, assuming an infinite transmission capacity. Ignoring losses, the energy component is the same as the LMP and equals the marginal generator's bid. The second component is known as the congestion component. This is the marginal cost difference of delivering one additional unit of electricity to a specific location with and without transmission limits. The third component is the loss component. This is the marginal cost of change in line losses to deliver one additional unit of electricity to serve a specific load. This component is usually insignificant. Question number 3. How does market optimization handle an overload? Although frequently used interchangeably, there are a subtle difference between an overload and congestion. A line is congested when the flow, or the expected post-contingency flow, is at or above its appropriate limit. When the flow or expected flow is above the limit, it's an overload. When there is an overload, the market optimization engine will dispatch available resources to mitigate it. However, the market optimization engine will try to keep the flow at the limit because the objective is to satisfy constraints with minimum cost. In other words, the optimization only tries to eliminate overloads. It doesn't eliminate congestion. Now let's look at sample answer. Given enough generation resources, the market optimization engine will dispatch generation resources to mitigate the overload. The optimization engine will try to hold the power flow or the expected post-contingency power flow at the line's capacity. Question number 4. Explain how the generators and the load get settled in the energy market. Settlement rules can be very complicated and can vary by markets. However, the basic rule is simple. The loads or generators pay or get paid at their local bus LMP. Now let's look at sample answer. In the energy market, generators and the loads are settled by the LMP at their local price node or aggregated price node. Many ISOs that run a day-ahead market and real-time market follow a multi-settlement system, one in day-ahead and one in real-time. As a result, market participants in both markets will be settled twice based on the LMP in each market. Question number 5. What is a shift factor and how does it work? Give an example. The shift factor is your best friend when it comes to congestion analysis and generation dispatch. Make sure you understand it. Let's look at the sample answer. The shift factor represents the change in the line flow due to a unit power injection at a node or bus in the grid. The shift factor can range from -1 to 1, or in percentage term, from -100% to +100%. For example, if a shift factor of the ith bus to the kth line is 0.3, it means that 1 unit of change in power injection at bus I will increase the power flow in line K by 0.3 unit. Question number 6. What are the main differences between a real-time market solution and a state estimator solution? The market solution and the state estimator solution have different scopes. When you compare them, make sure you compare apples to apples. Keep in mind that the market is always looking ahead. Now let's look at the sample answer. Real-time market solutions are look-ahead solutions. The dispatches and line flows in a market solution are operating targets based on expected future operating conditions. On the other hand, the state estimator solutions represents the current operating condition. Question number 7. All else equal, what can you say about the LMPs on the sending end and receiving end of a congested line? Please explain your answer. It is important to understand that the congestion contributor will receive a lower LMP, not a higher one. This mechanism uses prices as signals to redispatch market participating generators to mitigate overload and manage congestion. Now let's look at the sample answer. The LMP at the sending end tend to have a negative congestion component, and the LMPs at the receiving end tend to have a positive congestion component. This way, generators at the sending end are incentivized to keep or reduce their generation by receiving a lower LMP. On the other hand, generators at the receiving end are incentivized to generate more by a higher LMP. Question number 8. Can LMP be negative? If so, give some examples. However, each ISO has its admin price floor and price ceiling to make the problem solvable and prioritize constraints based on their importance. A negative price can be a result of both negative bids and congestion. Now let's look at the sample answer. Yes, LMP can be negative. The following conditions will lead to a negative LMP. First, if your marginal unit's bid is negative, then you will have a negative LMP. This is kind of the obvious scenario. The second condition is when congestion results in a negative incremental cost to serve the next megawatt of load at a specific bus. For example, the LMP will be negative $10 per megawatt hour if serving the next megawatt load requires increasing 2 megawatt of a $10 per megawatt hour generator and decreasing 1 megawatt of a $30 per megawatt hour generator. Question number 9. Can LMP be higher than the highest generator's bid? Please give an example. LMP are driven by the incremental cost of serving the next megawatt of load rather than the highest generator's bid. Hence, limiting the maximum LMP by putting a ceiling on the bid may not be effective when there is congestion in the system. Now let's look at simple answer. Yes, LMP can be higher than the highest bid of the generator if the congestion in the system makes the incremental cost of serving the next megawatt of load higher than the highest generator's bid. For example, the LMP will be $50 per megawatt hour if serving the next megawatt of load requires increasing 2 megawatt of a $30 per megawatt hour generator and decreasing 1 megawatt of a $10 megawatt hour generator. If these are the only two generators in the system, then the LMP is higher than the highest bid. Question number 10. Compare the uniform pricing and the pay-as-bid system. Which one will likely incentivize efficient generation? Please explain your answer. In the US, the energy market follows a uniform pricing model. Other market models, such as pay-as-bid, are also considered for wholesale electricity markets. From the market design perspective, it's critical to understand the pros and cons of each market design and discuss the regulation needed for each design to work properly. Now let's look at the sample answer. The uniform pricing system will likely incentivize generation efficiency because the market clearing price is set by the marginal unit. For example, with improved fuel efficiency, the marginal unit could lower its marginal cost, i.e., become intramarginal, and therefore become more profitable. All else equal, generators in a pay-as-bid system will have less incentive to lower their marginal cost, but to speculate by manipulating their bids. All right, I hope you find the questions and the sample answers useful. See you in the next video. Bye.